Hey, in this video I'll explain a paper called MiniCPM4, which introduces an ultra-efficient large language model designed to run directly on edge devices. Most large models today run on the cloud, which means high costs and latency. MiniCPM4 is designed to run directly on devices with limited resources, like Jetson or even smartphones. The authors improved efficiency in 4 areas: model architecture, training data, training strategy, and inference system. In a transformer, we calculate the attention score of each token with every other token in the sequence. For example, token 1 attends to token 2, token 3, and token 4. Token 2 attends to token 1, token 3, and token 4. Token 3 attends to token 1, token 2, and token 4. Token 4 attends to token 1, token 2, and token 3. This means the cost grows quadratically as the number of tokens increases in order of n squared. In this paper, author introduce INFLLM version 2, a sparse attention metard. Let's say you have 512 tokens, and for each token, you've calculated its key and value vectors. INFLLM then divides these into 8 blocks, with each block containing 64 key and value vectors. For each block, we compute a semantic kernel, which is simply the mean of all key vectors in that block. You can think of this as a summary or a representative vector for the entire block. We represent these kernels as S1, S2, S8, 1 for each block. Now, for any given query token, we will select relevant block for each query. To decide which blocks are relevant, we compute the similarity between the query queue and each semantic kernel SI using a dot product. We then select the top k most relevant blocks based on this score, and compute the attention scores only between the query token and the tokens within those selected blocks. This method keeps about 81% of the attention sparse, yet performs almost as well as full attention, while being much faster and lighter. Next, instead of training on noisy web data, the authors built an efficient filtering pipeline that distills trillions of tokens into a much smaller, cleaner dataset, achieving performance comparable to models trained on 36 trillion tokens using just 8.3 trillion. Let's walk through the high-quality data filter pipeline. Author use high-quality small-known data to pass this through the pre-trained small LLM to further filter the data. Filtered high-quality data helps seed recipes learn what good data looks like. The large, noisy web data first passes through the seed recipe, which selects promising samples, candidates that might be high-quality data. The candidate data is then filtered by a fast, non-LLM classifier to identify high-quality samples. Finally, the classifier's filtered data is passed through the pre-trained LLM to confirm and select truly high-quality samples. The low-quality data rejected by the LLM is sent back to update the seed recipe, helping it better learn what bad data looks like. This allows the LLM to be trained on less high-quality data, using fewer resources, while still achieving performance comparable to larger models. Next, for efficient hyperparameter tuning, author used Model Tunnel v2, which helped them tune hyperparameters without retraining the full model each time. To run MiniCPM4 efficiently on edge GPUs, the authors developed a highly optimized CUDA-based inference engine called CPM.cu, which leverages low-level CUDA operations and hardware acceleration. MiniCPM4 shows that with cleaner data, smarter architecture, and efficient training and inference, we can build powerful language models that run even on edge devices, without needing massive compute or data.